Hello everybody. This presentation is based on the paper Analysis and Implementation of Output Voltage Regulation in Multi-Phase Switched Capacitor Converters. The paper is authored by Professor Ben-Yaakov and Alexander Kushnerov. Switched capacitor converters use a number of switches to commutate so-called flying capacitors. In this simplest example, the flying capacitor C is charged by the input voltage source and then is connected in series with it and discharged to the load. Under no load condition, the output steady-state voltage will be twice the input voltage. The operation of this converter does not differ in principle from the operation of charge pump. However, the charge pumps use clocks and not switches and operate in open loop, meaning there is no regulation. Any switched capacitor converter can be represented by a simple equivalent circuit that includes a target voltage source and serial resistor. This resistor is called equivalent resistor and represents all the losses in the converter. Connecting the load to the equivalent circuit, we actually get a voltage divider. Consequently, the converter efficiency can be expressed as the ratio of the output and target voltages, or that is the same as the ratio of the corresponding resistors. It's evident thus that to regulate the output voltage one needs to adjust the equivalent resistor. This will affect the efficiency, and to obtain high efficiency the target voltage must be very close to the output voltage. Let's now consider the multi-phase SCC with the binary output voltage of 3/8 of Vn. The switching phases of the converter are represented by four topologies, where the input voltage source and the flying capacitors are connected in different ways. Each topology is determined by the corresponding row in the table depicted on the left. This table actually comprises a set of coefficients Aij taking the values of -1, 0, and 1, except of the first column, which defines the connection of Vn. When these four topologies cycle, the converter arrives at the steady state with constant binary voltages across the flying capacitors and constant output voltage of 3/8 of Vn. Due to charging or discharging of the flying capacitors, the power is lost in each topology. Using the average output current as a common reference, we can express each partial power loss as the square of the average output current times the corresponding partial equivalent resistor. Thus, the total power loss is equal to the square of the average output current times the sum of all the partial equivalent resistors. This implies that the total equivalent resistor is the serial connection of all the partial equivalent resistors. Once topology I is configured, a total capacitor Ci begins to charge or discharge through a total resistor Ri. This resistor represents the on resistances of the switches and the ESRs of capacitors. The time constant of topology I is defined as tau I, equal to RICI, while the time allotted for topology I is Ti. Now, the current through Ci is dependent of the relation between Ti and tau I. The charging of Ci is practically completed if Ti is at least 5 tau I, and this case is denoted by Cc. In the case when Ti is approximately equal to tau I, the charging is partial Pc, and if Ti is much smaller than tau I, there is no effective charging, Nc. The average current serves here as a common reference for all the three cases. Thus, for the same I average, the RMS of the momentary current is minimal in the NC mode, and therefore the efficiency of SCC operating in this mode is maximal. The objective of this study was to regulate the output voltage by duty cycle control, and the proposed approach is to adjust the value of equivalent resistor by varying the time slots Ti, while the total switching period Ts is kept constant. In the NC mode, the momentary current through each flying capacitor is rectangular. The RMS value of this current is determined by time slot Ti. For example, if we reduce the time slot from T2 to T1, the RMS of I1 will be higher, while the average of I1 and I2 is the same. The ratio of the RMS value of the momentary current and the average current is equal to Ts over Ti and denoted by Ki. Let's now consider the expression for partial equivalent resistor Rei. In the NC mode, the switching period tends to 0, and the asymptotic limit of the partial equivalent resistor is simply the square of some coefficient Mi times Ki times Ri. For the shorter time slot T1, the value of K1 is greater than K2, and therefore the partial equivalent resistor Re1 is also greater than Re2. As was shown earlier, each row in the table defines a given topology and therefore can be used to compose the steady-state KVL equation. This equation includes a term in brackets that controls the voltage drop across the total resistor Ri. In the steady state, the average current through each flying capacitor should be 0. On the other hand, the average output current is equal to VO over RO. This gives us two equations, which again use the coefficients Aij of the table. Summarizing the above, we arrive at system of two-folded equations. The first equation is in fact a set of 4 KVL equations, and the other is a set of 4 charge equations. Thus, we have 8 equations with 8 unknowns written here in matrix form. The considered matrix equation can be generalized and written in symbolic form. Here A is the incidence matrix, AT is its transpose, KR is the diagonal matrix, and GO comprises the single known zero element 1 over RO. Let's assume for simplicity that all the total resistors Ri are equal to R. Solving the above system, we find the conversion ratio V out over V in as a function of the factors Ki and normalized resistor P, which is equal to Ro over R. Now, we define partial duty cycles Di to be reciprocal to Ki and equal to Ti over Ts. An additional condition is that the sum of all the partial duty cycles should be equal to 1. Thus, the output voltage can be regulated by controlling some Di. The simplest regulation strategy is to define one topology as pivoting and select its duty cycle as master duty cycle D. All the rest duty cycles will depend on D and therefore are called slave duty cycles. The control algorithm can further be simplified by making all the slave duty cycles equal. The selected master duty cycle should produce smooth regulation over the required range. In the considered binary SCC, the required range is the gap between the conversion ratio of 3/8 and the lower next of 1/4. We tested each topology and role of pivoting and built 4 regulation characteristics. So, we have 4 candidates to master duty cycle. The red line here corresponds to D equal to D1 that provides the most linear regulation above 1/4. Thus, the first topology will be pivoting, and D1 will be the master duty cycle. The experimental setup following the above figure was built around the CMOS bidirectional switches with an on resistance of 1.2 ohm. To provide the NC operation at the limited switching frequency, an external resistor of 470 ohm was connected in series with C3. The rest of the parameters are listed here. The bottom figure shows the actual currents flowing in the topologies 1, 2, 3 and 4. These currents were measured as the voltage drop across the external resistor for the master duty cycle equal to 0.833. This figure shows the measured regulation characteristics, blue dashed line that agrees well with the calculated characteristics, red solid line. Note again that below the level of 1/4 we can switch the conversion ratio to 1/4. So, very high RMS values of the topology currents presented on the right can be eliminated. This figure shows how the voltages across the flying capacitors change with the master duty cycle. Note that under no load condition the terms in the large brackets tend to 0, and the voltages reach their nominal binary values. This brings me to the conclusions. So, the regulation is accomplished by increasing the losses. Besides of the master duty cycle, the regulation characteristic is also dependent on the ratio of the load and the switch resistances. As the load resistance increases, the regulation depth decreases, and at very light loads the regulation ability is lost. Thank you very much for your attention.